Lab 2, Motion of the Falling Object by Han-Bin Kim. The purpose of the lab was to apply the Newton's second law to the falling object and analyze how wave force and drag force acts upon the system. First of all, I created the falling object video with the tennis ball and used the height from the neck to the feet, which is 165 cm as indicator to show how much the ball fell. As you can see, the red dots are the center of the mass of the ball, and I used that to collect the data in the checker file. I will use the y data because the ball is falling in the negative y-axis. As you can see here, the red ones are the experimental velocity and the position which I got from the checker file, and the blue and the green ones are the model position and the velocity which I calculated using the formulas. The blue one is only the wave force and green one is the drag force added to the wave force. The formula I used are shown here. The force of the drag force is calculated with negative b times velocity, and wave force is calculated by negative mass times gravity, which is gravity is 9.7. I calculated the experimental velocity using the delta p over delta t, and I calculated the modal velocity by using the Newton's second law, which says the final velocity equals initial velocity plus f net divided by m times delta t. The modal velocity of the wave force only uses the formula of the wave force, mg, as the f net, while the velocity of the drag force added to it uses both wave force and drag force as net force. And in Python file, as you can see, I'll explain it briefly. The ball's mass was 0.057 kg, and ball's initial position was close to 0, and ball's velocity and time was 0. The delta t, change in time, was 0.05 second, and gravity was 9.8 miles per second squared. And the j hat, which indicates the direction of the ball, is in y direction. And the difference between the drag force added and the wave force only was the b, which is used in the force of the drag, and the net force used in the while loop. In the wave force only, the ball's mass times the gravity times j hat, which indicates the direction, was used. But in drag force added, we add the wave force and the drag force together to form the net force. So in the Python, you can see that red arrow is the wave force and the blue arrow is the drag force, and they are contrasting each other, causing the ball to slow down. So here is the graph. The blue is the experimental position, and the orange is the drag and the wave force, and the red is the wave force only. So as you can see, the red is in the bottom, and other two is in the upper position. What does it mean? It means that the modal position of wave force only is the quickest, and the modal position when the drag force is added to the wave force, the ball actually slows down. As you can see in the velocity versus time graph, the acceleration of the red, which is modal position with the wave force only, is faster, quicker than the modal position which has drag force added to it. And as you can see, the experimental position, the velocity, is much slower than the other two modal position. And in my opinion, this is caused by the drag force in the reality. The drag force in the reality actually is greater than the calculated ones, in my opinion, and therefore causing the ball to slow down much more than what it did in this modal position. Because tennis ball has volume, and that volume also causes the drag force. So, what if the axes are reflected? If the axes are reflected, as you can see, the red is the position of the original one, and blue is the reversed one, and the graph just reflects over the x-axis. Well, the data are the same, but the value, negative and the positive, are just reached. So in conclusion, I think the Newton's second law holds, and both drag force and wave force acts upon or affects the system. The drag force affects the system much more if ball actually falls for a longer period of time, because drag force uses the velocity, is affected by velocity, it is directly proportional, and velocity is directly proportional to the delta t, which is time, and for the ball to have greater time, it has to fall longer, which means that it is dropped from higher position. And wave force actually acts upon the system more if it is fallen for a short time, because wave force is constant throughout the formula or experiment, and therefore if it is fallen short amount of time, it affects more greater.